Hi everyone, welcome back. This mini lecture will continue our discussion of the Drude model, but instead of electrical transport, we'll talk about thermal transport. You know that metals conduct electricity very well, and probably that they also conduct heat very well. So asking what predictions can we make about thermal transport in metals in the framework of the Drude model makes sense as a good thing to ask. So let's start by reviewing some basic facts about thermal transport. So just like Ohm's law, which says that J equals sigma E, the electric current is proportional to the electric field, which itself is the gradient of an electric potential. Fourier's law tells us that a thermal current, JQ, is linearly proportional to a temperature gradient with constant of proportionality kappa. Kappa is the thermal conductivity of the material, just like sigma is the electrical conductivity. So let's compute thermal conductivity in the framework of the Drude model. So let's consider a one-dimensional rod of material with a temperature gradient. So here is this one-dimensional rod. Let's suppose there's a hot end and a cold end. And let's define the x direction like this. It's along the length of the rod. So let's consider the heat current at one point in the rod, x. So here's the point x in the rod. Now, electrons that are hot are going to be arriving at point x from the left side, and electrons that are cold are going to be arriving at x from the right side. Let's call v the average speed of the electrons. All right. Let's continue on here. So electrons coming from the hot side came from a location x minus v tau. So here's our rod, here's the point x, this is the hot side, and this is the cold side. So if an electron is arriving at point x from the hot side, it on average last scattered with an ion at time tau in the past. And if its average speed emerging from the collisions is v, it must have originated from its last collision at this point. Likewise, electrons coming from the cold side came from x plus v tau. Okay, so let's call E of t the energy per particle at temperature T. Okay, so what we'd like to now compute when we compute the thermal current is to compute essentially the energy current associated with electrons in this system. So remember that the electric current J is minus NeV. So N is the number density of electrons, E is the charge per particle, and V is the speed. Now to compute a thermal current, JQ, we're going to compute it in the following way. And so let's compute the current, the thermal current resulting from electrons coming from the hot side, from the left side. So this is JQ minus. We'll call this N over 2. Why is it N over 2 as opposed to N? Well, half of the electrons roughly are coming from the hot side. The other half are coming from the cold side. Okay, they're coming with speed V. We've assumed that this is the average speed per electrons. What is it that they carry? Well, in this case, we're not interested in the charge they carry, but rather the energy that they carry. So we're going to use E. Remember, this is the energy per particle at temperature T. This notation will persist throughout the course. So there's the temperature of the hot electrons. We're imagining that there's a thermal gradient along this wire, so we should specify the temperature at which we're thinking about here. So we're thinking about the temperature at position x minus v tau. Remember, this is the position from which the hot electrons came. The energy of the hot electrons arriving at position x really is determined by where they came from, which again is this location x minus v tau. So now the thermal current coming from the cold side, JQ plus, is N over 2 V E, now at T of x plus V tau. So the total thermal current JQ is JQ minus JQ plus. This is the thermal current associated with electrons moving to the right. This is the thermal current associated with electrons moving to the left. So this is N over 2 times V. Now E of T x minus V tau minus E of T and x plus V tau. So hopefully you can see that this object looks like it's certainly a change in energy as a result of a change in position. This is something like a derivative. It's like a derivative multiplied by a small change in position. So with that realization, let me write this as this. So this object again is a change in energy resulting from a change in position and the temperature gradient along that profile. So this change in energy can be written as dE dt, dt dx times a small change in position to V tau. So let's write it as minus NV squared tau dE dt times dt dx. All right, so let's make some simplifications here. So note that V squared in this calculation is a one-dimensional average velocity. If we want to go to 3D, we should note that the average component of velocity in the x direction, Vx squared, is equal to Vy squared, which is equal to Vz squared, is each of them is a third of the square three-dimensional velocity. Let's also note that little n, the density of electrons in the system, times dE dt, the variation of the energy per particle divided by, with respect to temperature. This is big N over big V, the total number of electrons divided by the total volume, times dE dt. Well, this is the same thing as 1 over big V times d capital E dt. This is the total energy of the system. But this is nothing more than CV, the specific heat of the system. So altogether then, JQ, let me now go to 3 dimensions, is minus a third V squared times tau CV times the temperature gradient like this. So we can identify the thermal conductivity as 1/3 V squared tau CV. So this is the thermal conductivity in the framework of the Drude model. You see that this equation here is of the same form as Fourier's law. J is proportional to the gradient of the temperature T. Constant proportionality, again, is the thermal conductivity. Now, one thing that's maybe a little disappointing about this is the presence of this relaxation time tau in the expression for the thermal conductivity. Remember, in the Drude model, we don't know where tau comes from. We must assume its presence to think about things like dissipation. We're always a little disappointed, though, with any specific predictions that depend on tau, because again, we don't exactly feel comfortable with its origin. So sometimes in the Drude model, we try to find predictions that do not depend on tau. So let's try to do that. Let's do it in the following way. Let's compute kappa over sigma. Kappa is the thermal conductivity. Sigma is the DC Drude conductivity. So this is 1/3 V squared tau CV times M over N V squared tau. You see that the taus are going to cancel. So this is 1/3 V squared CV times M over N V squared. So that's nice. We don't really have a great feeling for what CV should be, but in the Drude model, at least, we're thinking about the electrons as members of a classical gas of particles. So it's not so hard to imagine that we could use equipartition to estimate the average energy of the gas of particles at some temperature T. So it might make sense to assume that the average value of a half mv squared is 3/2 kBT. We talked about this before. This would lead us to suppose that the average value of V squared is 3 kBT, and the average specific heat is 3/2 times little n the density times Boltzmann constant Kb. Now, if we substitute these values in for V squared and the specific heat, we find that the ratio of kappa over sigma, where we divide out the temperature T, is equal to 3/2 Kb over E squared. So this is called the Widowman Franz Law. And it says that the ratio of kappa to sigma times temperature T does not depend on temperature, nor does it depend on the relaxation time tau. This is predicted to be true when it's electrons that carry heat, which is not always true. But when it is, this law is remarkably accurate. Okay, and this is actually quite surprising for 2 reasons. First is that this estimate for the mean square velocity is actually vastly too small. As we will see in the coming lectures, the reason that it's too small is that it completely neglects quantum mechanical effects of the Pauli exclusion principle on the electronic velocities. If you like, we've assumed that all of the electrons can occupy the ground state, when in reality, you know that that's not true due to the Pauli exclusion principle. There's also a sort of simultaneous error here, which is fortuitous, which is that our estimate of CV is actually much too large in the Drude model. So our estimate of V squared was much too small. Our estimate of CV is too large. These errors sort of fortuitously cancel each other out, leaving us with the Widowman Franz law in a form like this, and it is actually remarkably accurate. So this is another one of the triumphs of the Drude model. Not only does it not depend on the relaxation time tau, but given these two fortuitous errors that cancel each other out, the numerical result is quite close to reality. So there's one more thing we can talk about, which is that you may have noticed that we neglected the difference in velocity with temperature of the electrons. We assumed that they had the same velocity, which was independent of temperature over a small range. That doesn't affect our calculation of the that does not affect our calculation of the thermal conductivity so much, but it leads to something called the Seebeck effect, where a temperature gradient can cause an electric field. So we just saw, we just talked about thermal conductivity, where a temperature gradient drives a heat current. There is a related effect where a temperature gradient creates an electric field. So let's talk about this now. This is the Seebeck effect. Let's consider again our one-dimensional bar of electrons with a hot end and a cold end. Now, the cartoon picture here is that electrons traveling from the hot end are traveling faster than electrons traveling from the cold end. So if we sit at some point x here, we'll have more electrons sweeping by us from going from left to right than those going from right to left. That will lead to an electric field that builds up. So again, the cartoon picture for thermal conductivity is that we have electrons carrying more energy from the hot side than the cold side. That leads to an energy current. Now we're thinking about the charge degree of freedom of the electrons. There are more coming from the hot side than the cold side, or they're traveling faster. That leads to an electric field. So let's describe this effect where we have an electric field that builds up in response to a temperature gradient T. Q is called the thermal power. It is the constant in proportionality. Let's again consider what happens to this point at x. So now let's compute the velocity of charge carriers, the net velocity of charge carriers at this point x. So it will be half of the sum of the velocity of electrons coming from the left and the velocity of electrons coming from the right. So the electrons coming from the right have a negative velocity. The velocity they have depends on where they made their last collision, which is x plus v tau. The velocity of electrons coming from the left-hand side is positive, and it depends on the position of the electrons at their last collision, which is x minus v tau. All right, so we can write this as minus tau v dv dx. Let me now play a trick and write this as minus tau d by dx of v squared over 2. Let's jump to 3 dimensions. Now I'm adding a vector symbol because we're in 3 dimensions. This is minus tau over 6 d2v by, well, let's see. It's minus tau over 6 times dv squared dt times the gradient of the temperature T. All right. So I've expanded our one-dimensional derivative dv squared over 2 dx into now dv squared over t times the gradient of the temperature T. And so this is now the net velocity of charge carriers in response to a temperature gradient along this wire. But of course, this velocity will not persist indefinitely. An electric field will build up, which cancels the net velocity of charge carriers. We can't have charges moving. We can't have charges moving preferentially in one direction forever. This electric field will build up to cancel this. So the electric field that builds up E will be such that the velocity induced by that electric field VE, which is minus E tau over m, exactly cancels the velocity associated with the temperature gradient. So this means that minus E tau over m is equal to tau over 6 ev squared dt times the gradient of t. So this is now of the form E equals Q times the gradient of T. We're trying to find Q, the thermal power. We can read it off. It is minus m over 6E dv squared dt. Okay, let me play another trick. It's minus 1 over 3E d by dt of mv squared over 2. mv squared over 2 is the energy per particle. If I divide by the density, then this becomes the specific heat. This quantity in parentheses, if I multiply by the total density, becomes the specific heat of the system. All right. So in this case, our calculation for the thermal power does not have this fortuitous cancellation between CV and V squared. The observed thermal powers that one finds in experiments are about 100 times smaller than what one would predict. Again, that's because the naive estimate, when you think about electrons as part of a classical gas for the specific heat, is much too large. The actual specific heats are much more smaller. All right. So this ends our discussion of the Drude model. We'll continue with our discussion of the Sommerfeld model next time. This is when we start to relax some of the assumptions of the Drude model. The first assumption that we'll relax is that the electrons have to be classical. We will start to consider some of the basic quantum mechanical properties of electrons in the next lecture.